The message is even grimmer in some results. All that's hundreds of millions of years off. No big deal. But I suggest to you that something coming at us is not hundreds of millions of years off, not even thousands of years off potentially, but could be staring us in the face, and that's the end of the interglacial. The interglacial is the time between glaciations on planet Earth. In the Pleistocene, the last 2.5 million years, we've had on average 90,000 years of ice, 10,000 years of warm. We've just finished 10,000 years of warm. Given everything else that we know, we should expect very soon to have ice. The transition from warm to ice can take as little as 20 years, according to the Ice Core record. 20 years we could go from interglacial to glacial. Now, I guarantee you, you don't want a glacial interval. The first thing is there's so much dust in the air you can't use jet engines. So we have to take propeller planes everywhere. Well, that alone is enough not to have another ice age. I once took a Pan Am Clipper from Seattle to Hawaii in 1956, and it took 13 hours. And my mother was certifiably insane after 13 hours with a kid in an airplane. You don't want to go back then. But the second thing is, when ice happens, what happens to our ability to feed ourselves? Bill Calvin has talked about changing the great climate flip-flops. What happens when we go from interglacial to glacial to Europe? Because Europe is anomalously warm because of a thermal current going up the coast. The first thing to go is that current. And 700 million Europeans who can now feed themselves all of a sudden can't. And then we have 700 million heavily armed, cranky Europeans, all nuclear armed, who have to go somewhere. And where are they going to go? Well, they're going to go south. Everybody's going to go south. All of humanity has to go south or north and get squashed into the equatorial regions. The end of the interglacial may be not the end of humanity, but could spell the end of civilization as we know it, because of the chaos and the rapidity over which it could take place. And I will be the first to get fired by suggesting that global warming is a very good thing. Unless, of course, it creates the end of the interglacial, which we don't know if that's the case or not. Well, barring that catastrophe, then we wait hundreds of millions of years, and we get the end of plant life, animals, loss of the oceans, end of all life, and the enlarging sun. So that's our fate, at least as we can predict it. Well, that's a long time away. A lot of that stuff. It suggests to us, this horrible, grim message, that we're living in a pretty wonderful moment, not just in the 100-million-year context, but in the 1,000 and century context, that this moment in time is a very brief one. And already we're seeing the changes that our species has produced. Here is a Norway rat, now introduced to Hawaii, being introduced to a soon-to-be extinct flightless rail. And we certainly know what happened when Europeans made it to North America with the Clovis tip points and the disappearance of these. So I guess my message here, try to be as upbeat as possible. It's almost like new age, squishy, and I hate that stuff. But nevertheless, really appreciate this moment in time, this moment in your lives, because all of you will be a year older next year. And it's probably better now than then. Unless, of course, you're 14, it'll be better then than now. But for all of you who go to the doctor with that downward spiral, just as our Earth is, this is not a bad moment to be here. And I appreciate your coming and listening. Thank you.
Thank you, Peter. We're going to take some questions in just a moment. I'm going to ask you to please stand up and speak loudly. We will repeat the question so that all can hear. So let's start with some questions. Who's got some really good questions? Or bad ones. We'll take those too. First row.
Hi. Earlier in the slide presentation, we saw a slide that showed two graphs against each other, one showing the amount of iridium in that small slice of sediment compared to the extinction. Right after it got out of that area, there was like a plateau of life and then another drop-off again. Can you explain what that was about?
Yeah, what we're looking at there are both new species arising and survivors. So in that particular slide, we're looking at microfossils. And as things die off, others arrive to take their place. So this plateau and this re-origination is a natural part of every mass extinction. Things hit a minimum, and then they go off again. Question, please.
The amazing stability of temperature on this planet, would you say something about why?
Yeah, I alluded to this, and I didn't want to go into it in detail, but I think I will here. I keep talking about plate tectonics. We know what that is. That's a case where the Earth at spreading centers pulls apart, new magma comes up. But in areas, other plates descend down. Off the Pacific coast, this happens. Off South America, the Andes Mountains, we always get mountains in front of it. And as plates dive down, they carry with it limestone and rocks and other material which partially melts. That melt comes up as granite. It also comes up as carbon dioxide. We recycle then the calcium carbonate and the granite material itself so that as this material dives down, the raw materials necessary to build limestones are brought back to the surface again. When the Earth gets warmer through too much carbon dioxide, we build lots of limestone. That's why we find in the tropics coral reefs and not in the cold areas. If the whole world gets really warm because of too much carbon dioxide, there's lots of limestone everywhere. The limestone pulls CO2 out of the atmosphere, and this particular process lets us bounce back and forth at a constant temperature. It's just like a thermostat. Your furnace, it overshoots a little, it then gets cool, it gets warm, it gets cool. Carbon dioxide in the atmosphere makes us warm. Pulling it out through limestone formation makes us cool. It's this process that only can take place because of plate tectonics. On non-plate tectonic worlds, we don't think it can happen. Why do we have glaciation? Well, glaciation is when screw-ups occur. And the screw-up that occurred is that if you get too much weathering, you get much more calcium going into the system. You build enough limestone to really pull it down. When the Himalayas went up, the Himalayas are an aberration. It's the thickest continental crust in the world. A continental plate went up at a continental plate. That rarely happens. The Himalayas, the tallest mountains in the world, are eroding so fast, they're causing CO2 to get sucked out of the atmosphere faster than it normally does. It caused a big dip in CO2, which cooled us enough to create glaciation.
And how long will that go on?
Another 2 to 3 million years. And hopefully it's over.
So we should all buy extra.
No, but I think, this is the nightmare scenario, because it's a coin flip right now. The coin flip is if we don't do anything and we dip into glaciation, we're screwed. But if we do something, it could also dip us into glaciation. We don't know if putting CO2 into the atmosphere through man-made activities is going to create a glacier faster or slower than otherwise. We don't know. It's a total coin flip. If we do the wrong thing, we're going to create the glaciers. By the way, there's a Hollywood blockbuster for next summer about this scenario. We do the wrong thing and the glaciers come. This is a Spielberg movie. You've heard it here first. Question in the back, please. You, yeah, you.
Given that bacteria survive through a lot of bombardments and a lot of the life of the Earth, is your position then that bacteria can form fairly easily on other planets?
It's my guess that life is easy to form. I think it formed over and over and over on this planet in the heavy bombardment period. The scary thing, of course, is no one in a laboratory has been able to do it since. But given the amount of time, if you think of the conditions necessary to do this, having millions of years, there's no laboratory chemist who has that time period to play with. Given that said, this is why I think that bacteria are probably pervasive throughout the universe. Plus, they can move from place to place pretty readily. The experiments from Caltech now, they've got big guns and bombs. They put bacteria in these shells and they explode them against walls, simulating impact conditions. They survive. They can survive if they're buried a little bit in a hunk of rock. So from Mars to Earth, a living bacteria easily makes it. This is panspermia. Sooner or later, you've got to come up with a thesis, a hypothesis of how life started in the first place. But once started, it can move around. I think this is pretty clear. Question, please.
What effect does the undestructible tropical rainforest have on the survivability of the planet?
Yeah, what effect does tropical rainforests have on survivability? It's a couple. As we remove rainforest, that soil is very thin, and it gets replaced quite often by bare rock. And that bare rock itself changes the albedo of the planet, the whole ratio of sun hitting. Forests absorb a lot of light. Well, a lot of light bounces back into space once that happens. Secondly, we remove, obviously, the amount of oxygen that's present. I think the oxygenation question is also a very key one, and one that I think is very scary for us. Everything we're doing is probably wrong. Yes, little girl back there, big girl. Oh, I didn't mean to call you a little girl.
Could you clarify what you meant by what would happen with hydrogen?
Yeah, well, this is a guess that Titan will get warmed up when the sun goes red giant. And Titan right now has frozen ethane